This is section 7.1, part C, describing sample distributions. The fact that statistics from random samples have definite sampling distributions allows us to answer the question, how trustworthy is a statistic as an estimate of a parameter? To get a complete answer, we consider the shape, center, and spread of the sampling distribution. For reasons that will be clear later, we'll save the shape for last. So when you're looking at the center, you have to decide if it's a biased or an unbiased estimator. Let's return to the familiar chips example. How well does the sample proportion of red chips estimate the population proportion of chips if the population proportion is 50%? The dot plot below shows the approximate sampling distribution of p hat once again. So as we can see, p hat is the proportion of different samples and what proportion of the sample is red. So if we take a bunch of different samples and we look at what proportion of that sample is red and we graph it, this is the graph that we would end up with. We noted earlier that the center of this distribution was very close to 0.5, which is the parameter value. In fact, if we took all possible samples of 20 chips from the population and we calculated their p hat for each of those samples, then we would find that the mean of all those p hat values would be exactly 0.5. So for this reason, we say that p hat is an unbiased estimator of p. A statistic used to estimate a parameter is an unbiased estimator if the mean of its sampling distribution is equal to the true value of the parameter being estimated. So since we know if we take all samples that are possible of size 20 and we're going to get the mean of all of those together equals the actual mean of the population, then it's safe or it is unbiased to use the mean of a sample to estimate the mean of our population. The value of an unbiased estimator will sometimes exceed the true value of the parameter and sometimes be less than if we take many samples. Because its sampling distribution is centered at the true value, however, there is no systematic tendency to over or underestimate the parameter. This means that the idea of lack of bias in the sense of no favoritism more precise. The sample proportion p hat from a simple random sample is always an unbiased estimator of the population proportion p. This means that it's a very helpful result if we are dealing with a categorical variable like color. With quantitative variables, we might be interested in estimating the population mean, median, minimum, maximum, Q1, Q3, variance, standard deviation, IQR, or range, which, if any of these, are unbiased estimators. So if we were to do this example, you would take a small piece of cardstock for each student in the bag, and you will use the population of the quantitative data to investigate whether a given statistic is unbiased. So each student would write their name and their height in inches neatly on a piece of paper of cardstock and then place it in the bag. Then I would mix up the cards, and you would draw out a sample of 4 cards, record the names and the height of the 4 children that you chose, put them back in, mix them back up, and the next student would do this. And we would have at least 25 people take these samples, and if we didn't, some people would have to take 2 samples each. From there, we would find the max and min. So we had the range, and we would take the means. So we'd find the mean of each sample and the range of each sample that was taken. And then we could plot those. And then we would compare the distributions. So when Mrs. Washington's class did this, the sampling height activity, they produced 3 different graphs. So the population distribution, this is the actual population, they had a mean height of 66.07 inches and a range of 21 inches. Now, when they took samples, the approximate sampling distribution, remember this can't be just the sampling distribution because it wasn't all possible samples of size 4, but their approximate sampling distribution is as shown, and they got a mean of 65.67. But when they looked at their ranges, the mean of all their ranges was 10.12 inches. So her students concluded that the sample mean is probably an unbiased estimator of the population mean, but the range is not unbiased. So the range is a biased estimator of the population. That's because the center of the distribution for its statistic was 10.12, which is much less than the corresponding parameter value of 21 inches. To confirm the class's conclusions, we used Fathom software to simulate taking 250 simple random samples of size 4 students, and in each sample we plotted the sample mean and the range of their heights from the sample. The graphs below show the population distribution and the approximate sampling distributions of the mean and of the range. And again, our means, if you take a look at the means, the actual population mean is 66.07. On our sample, the mean of all our samples, we ended up with 66.15. And our range for the entire population was 21. But for our sampling distribution, our approximate sampling distribution, they only got a mean for the ranges of 10.21. So it looks like the class was right. The X bar is an unbiased estimator of mu, but the sampling range is clearly a biased estimator. The range is the sample heights tend to be much lower on average than the population range. To get a trustworthy estimate of an unknown population parameter, start by using a statistic that's an unbiased estimator. This ensures that you won't tend to over or underestimate. Unfortunately, using an unbiased estimator doesn't guarantee that the values of your statistic will be close to the actual parameter value. So television executives and companies who advertise on TVs are interested in how many viewers watch particular shows. According to the Nielsen ratings, Survivor was one of the most watched television shows in the United States during every week that it aired. Suppose that the true proportion of U.S. adults who watch Survivor is 37%. In the figures below, the one on the left shows the results of drawing 100 simple random samples of size 100 from our population that had a parameter of p equals 37%. The figure on the right shows 1,000 simple random samples of size n equals 1,000, and then it found its sample proportion. So the one on the left is centered at 37, but it is much more spread out. The one on the right is still centered at 37, but it is much more compact. We can see that the spread of the figure on the right is much less than the figure on the left. With sample sizes of 100, the value of p hat vary from 22% to 53.5%. The standard deviation of the p hat in the figure on the left is about 0.05. Using a simple random sample of size 1,000, the values of your p hat only vary from 32% to 42%. And on the figure on the right, the standard deviation is about 0.015. So most random samples of 1,000 people give a p hat that is within 0.03 of the actual population parameter of p equals 37. The sample proportion, p hat, from a random sample of any size is unbiased estimator of the parameter p. We can see from the previous examples, those large samples have a clear advantage. They are much more likely to produce an estimate close to the true value of the parameter. So another way to look at this is larger random samples give us more precise estimate than smaller random samples. That's because a large random sample gives us more information about the underlying population than a smaller sample does. There is a general rule for describing how the spread of sampling distributions of a statistics decreases as the sample size increases. In sections 7.2 and 7.3, we'll reveal these rules for sampling distributions of p hat and x bar. One important and surprising fact is that the variability of a statistic in repeated sampling does not depend very much on the size of the population. The variability of a statistic is described by the spread of its sampling distribution. This spread is determined primarily by the size of the random sample. Larger samples give smaller spread. The spread of a sampling distribution does not depend on the size of the population as long as the population is at least 10 times larger than the sample. So you need to be cautious. Taking a larger sample doesn't fix bias. Remember that even a very large voluntary response sample or convenience sample is worthless because of the bias. We can think of true value of the population parameter as a bullseye on a target, and of the sampling statistic as an arrow fired at the target. Both bias and variability describe what happens when we take many shots at a target. So bias means that our aim is off and we consistently miss the bullseye in the same direction. Our sample values do not center the population value. High variability means that repeated shots are widely scattered on the target. Repeated samples don't give very similar results. So if you are biased, your answer may be really precise. You may have all of your data points really close together, but they're not accurate because they're nowhere near the bullseye. And if we have high variability, that means they're going to be scattered all over the bullseye. It may be centered around that center, but the data values aren't very close together, so they're not going to give you very accurate results. Notice that low variability, shots that are close together, can accompany high bias. Shots are consistently away from the bullseye in one direction. And low or no bias, shots that are centered at the bullseye, can accompany high variability, which means they have a wide spread. Ideally, we would like our estimate to be accurate, which means it's unbiased, and precise, so it has low variability. Students were asked to come up with different methods for estimating the number of tanks the Germans had in World War II based on several numbers of seized tanks. So the first way they're going to look at it is they're going to take the maximum plus the minimum. The second way they're going to look at it is they're going to take the mean plus 2 times the standard deviation. The third way they're going to look at it is twice the number of the mean. The fourth way will be twice the number of the median. And the fifth way is going to be the teacher's estimating tool. So below are the results of taking 250 simple random samples of 4 tanks and recording the values of the 5 statistics from each of the samples. The vertical line marks the actual value of the population parameter, which is N, and there are 342 tanks in the bag. So which of the 4 statistics proposed by the students' teams is the best estimator? And you need to justify your answer. So if you take a look at all the different estimators, the max-min, which is the maximum plus the minimum, appears to be unbiased. It is roughly symmetric and has the smallest variability among the student teams. It would generally produce estimates that are closer to the actual number of tanks. What was the partition method? Why was the partition method, which was used, that is 5/4 times the maximum, recommended by the mathematicians in Washington, D.C.? So if you take a look at that method, you can see that it is clearly skewed to the left. This is an unbiased estimator and has much less variability than any other student statistics. So it is a lot more compact, but it is very heavily skewed to the left, which means the statistic is more likely to overestimate than underestimate the number of tanks. Now, it would be good to overestimate the number of tanks so that the U.S. Army would not be taken surprised by the number of tanks. If you overestimate, you can plan for more, but if they were to underestimate, they may not have enough resources and supplies they needed to be able to handle the tanks. So let's check our understanding. The histogram above on the left shows the interval in minutes between eruptions of Old Faithful geyser for all 222 recorded eruptions during a particular month. For this population, the median is 75 minutes. We use Fathom software to take 500 simple random samples of size 10 from the population. The 500 values of the sample mean are displayed in the histogram above on the right. The mean of those 500 samples has a median value of 73.5. Is the sample median an unbiased estimator of the population median? And justify your answer. So if we take a look, it does appear that this is skewed to the left. So the median does not appear to be an unbiased estimator of the population median. The mean of those 500 samples is 73.5, where the actual median is at 75, and this data is skewed to the left. Suppose we take a sample of size 20 instead of size 10. Would the spread of the sampling distribution be larger, smaller, or about the same? With larger samples, the spread of sampling distributions is smaller. So increasing the sample size from 10 to 20 will decrease the spread of the sampling distribution. Describe the shape of the sampling distribution. Explain what this means in terms of overestimating or underestimating the population median. The sampling distribution, as we already said, is definitely skewed to the left. This means that in general, underestimates of the population median will be greater than overestimates.